Okay, so to start, our function is y equals negative x squared plus x all over x squared minus 3x plus 2. So first, we'll start off with the asymptotes. So you can actually simplify this function into negative x times x minus 1 over x minus 2, x minus 1. And before you find the horizontal or vertical asymptotes, you can actually cross out the x minus 1 on the numerator and denominator. And that will actually give you a whole for this function. So you can put x minus 1 equal to 0 or x equals 1. So you can put that under the asymptotes. So you have a whole at x equals 1. And then to find the horizontal asymptote, you look at the degree for the numerator and denominator, and they're both 1, so you can divide their coefficients. So for the numerator, the coefficient would be negative 1, and for the denominator, it would be 1. So your horizontal asymptote will be y equals negative 1. And then for your vertical asymptote, you can look at the denominator and put that equal to 0. So it would be x minus 2 equals 0, where x equals 2. And that will be your vertical asymptote. And I like to draw mine in a different color for the graph. So the horizontal asymptote will be at y equals negative 1. And the vertical asymptote will be at x equals 2. Next, we'll look at the intercepts. So we'll go back to the original function for this one. So for the y-intercept, you want to make x all the x's equal to 0. So for the numerator, you have y equals 0 squared plus 0. So that would just be 0 on the numerator over 0 squared minus 3 times 0 would just be 0. So you add the 2. And for your y-intercept, you would just get 0, 0. And then for the x-intercept, you will make y equal to 0. So you have 0 equals negative x squared over x squared minus 3x plus 2. You'll multiply both sides by the denominator, and you'll get 0 equals negative x squared plus x, where x equals 0. So again, you'll get 0, 0. And you can add that point on the graph for the intercepts. And then from here, we'll do the domain. It'll be negative infinity to 1. We're looking at the x values. So it'll be negative infinity to 1 because of the whole at x equals 1. And then you'd go 1 to 2 because it goes from the whole to the vertical asymptote, and then you go 2 to infinity because that's where the graph will finally end, or will end. So you finish the domain, the intercepts, and the asymptotes, and then lastly look at symmetry. And just to save time, you just have to trust me on this one. For the symmetry, when you plug 1 in for the x values, and then you plug in -1, you don't get the same answers. So it can't be an even function. And when you plug in 1 and -1, you also don't get the opposite signs. So it wouldn't be an odd function. So for the symmetry, it would be neither odd nor even. So those are the first few parts before we get into the real math part of it for the domain, intercepts, symmetry, and asymptotes. And then for the next part, we'll go on to Nick.
So you will end up doing the same thing as you did for increasing and decreasing intervals. You'll have to make a little like line chart here, except this time you'll be using the second derivative. So we have our chart here, and we also have to find points, just as we did in this place, and they end up coming out to be the same exact points, so that makes it a bit easier. We have -2, -1, and 1, and that means we could just use the same numbers that we did before to plug in. And once we plug in, we almost get the same thing, except we have 3 positives here, so that means it would be concave up at these points. But we have a minus here, which means it will be concave down from 3 over or 2 over, which is where the asymptote is. So once we've done that, it makes it a whole lot easier to graph. So just to start off, we know that since it's going to be concave down from here on over, we can just kind of make our 2 arrows here to start the graph on this part. And then since it's concave up from -infinity to 2, we can start to do this. So now we kind of have a general idea of what our function is going to look like. So just kind of have to connect. Remember, there's a hole here at 1. So that's part of it right there. And then second part, it's always increasing. This part's concave down, like we saw here. And this part is increasing, also concave up, like we saw here. There's no local min-maxes, and yeah, that's how you would sketch this curve for this rational function. Alright, so moving on to concavity, it is basically, you have to do it the same way you find the intervals, except this time we'll take the first derivative, which was 2x squared minus 4x plus 2 all over x squared minus 3x plus 2 and all that squared. So it's just the same steps now. You have to find the second derivative again, which comes out to a pretty large rational function. So that comes out to, take the second derivative, and this comes out to -4x cubed plus 12x squared minus 12x plus 4, and all that is over x squared minus 3x plus 2, and that is cubed. So the first derivative comes out to 2x squared minus 4x plus 2 over x squared minus 3x plus 2, and that entire thing is squared. So since we're trying to find the increasing or decreasing intervals, we have our derivative now, and we just need to find the critical points. So again, this takes a bit of time, so again, to make it simpler, you have to trust me on this. The critical points are x equals plus or minus 1 and x equals -2. So from there we can kind of just make a little like line chart. And then we can plot our 3 points down and 1. And from there, we have to find points that are either less than or in between these points into the derivative. And if the derivative, if that comes out to be negative, that means it's decreasing. Or if it comes out to be positive, that means it's increasing. So after we do this, let's see, if we just take -3 here, and then in between -2 and -1, we could just take -1.5. In between -1 and 1, we could take 0. And greater than 1. If we choose 2, it'll make this thing undefined because there is a vertical asymptote at 2. So let's just take 3, make it easier. And once we do this, everything comes out to be positive, so we know that it is increasing everywhere. And that makes this pretty easy, and also tells us that there are no local mins or local maxes, because if there were, we would see a negative in here, because then it would switch from increasing to decreasing, and then back to increasing, which means there would be a max or a min. We start with the original function. Which is that. And we have to use the quotient rule, take the derivative, which takes a long time. So just to make it easier and save space, this is what the derivative comes out to, first derivative. All right, so moving on to the last 3 steps of graphing a rational functions curve. Micaah already went through the first 4 with domain, intercept, symmetry, and the asymptotes, and everything's also here on the graph. We have our intercept here and our hole here, and then our 2 asymptotes here. So moving on to intervals.